Hi everyone, and welcome to our lecture video all about electromagnetic radiation. By the end of this lecture, you will be able to quantify the wavelength, energy, and frequency of photons of light. So to get us started with introducing some vocabulary, electromagnetic radiation is one of the ways by which energy travels through space, and we can describe electromagnetic radiation utilizing three different characteristics. The first of which is wavelength, which the variable of is this character lambda, which is a Greek symbol. So lambda is the wavelength and is characterized as the distance between two peaks or troughs in a wave. On the next slide, I'm going to show you different pictures of what our different electromagnetic waves can look like, and I'll characterize it by wavelength and frequency as well. But to introduce what frequency is, it is by this Greek symbol nu, and it points to the number of waves or cycles per second that pass through a given point in space. If we characterize wave length, length indicates that it is a distance. So our common units are going to be in meters or some sort of meters, nanometers, centimeters, different types of meters. Frequency, it's the number of cycles per second. So our units for frequency are going to be 1/seconds, or that's also known as 1 hertz. So you're going to see frequency used as 1/seconds, or we can call that inverse seconds, or a hertz. Lastly, a characteristic of our wavelength is speed, how quickly something is moving. And in our natural universe, the speed of electromagnetic radiation is the speed of light, which is the variable c, and is 2.9979 times 10 to the 8th meters per second. We can go ahead and utilize this value here for our speed of light as 3.00 times 10 to the 8th meters per second. Emphasis on the units here. It's some sort of distance over time, so it's meters per second. These are our three different characteristics, but looking at how this affects different waves, we can understand that waves are cyclic. There are peaks, and we can identify that the peaks of these waves appear at the top of our wave, versus a trough, which occurs here at the bottom. Based off of our definition of a wavelength, it's the distance between two peaks or two troughs. So we can notice here that one wavelength is the distance between here and the distance between here. That is one wavelength of our specific wave. Looking at the frequency, which is nu, we're told that it's 4 cycles per second, or 4 hertz. The reason we can identify that is we have 1 cycle right here, 2 cycles right here, 3 cycles right here, and we have a half of a cycle here, and the last half of our cycle here. So that adds up to our 4th full cycle. We see that there's 4 iterations of that wave, so it has a frequency of 4 inverse seconds or 4 hertz. And what we notice here, if we compare using some different colors, if I compare number 1 in red to number 2 in green to number 3 in blue, we notice something. We notice that our wavelengths are decreasing, right? We notice that our wavelengths are decreasing going from 1 to 2 to 3. So we can say from 1 to 2 to 3, we notice that our wavelengths are decreasing, meaning that the distance between the two peaks or the two troughs are getting smaller. And we also notice that even though I'm decreasing my wavelength, I'm having more cycles. It's a kind of a stronger wave we can think of. So we have an increased frequency. And we're going to talk more about that relationship in just a moment. But as a reminder, Wavelength is the distance between the peaks or troughs of our wave, and our frequency is how many cycles it goes through per second. So we can identify that relationship that we just described. There's an inverse relationship between my wavelength and my frequency. So between lambda and nu. The inverse relationship means that as we increase the wavelength, my frequency is going to decrease, and vice versa. If I decrease my wavelength, my frequency is going to increase. We saw that visually, but let's describe that mathematically now. This symbol right here means proportional. So if my wavelength is proportional to 1 over my frequency, that means that they are inversely proportional. And we can identify this mathematically by saying my wavelength times my frequency. We can multiply those together and set it equal to some sort of constant, that constant being the speed of light. So let's talk a little bit about how we can utilize that to give us even more information. Visually, this is what our electromagnetic radiation looks like. Gamma rays have the smallest wavelength. The longest wavelength are different types of radio waves. That means that gamma rays, if they have the shortest wavelength, they have the highest frequency. And radio waves have the longest wavelength, so it has the shortest frequency. And we can see here that our visible light exists in this electromagnetic spectrum of our different electromagnetic radiation. Our blue light has a wavelength of 4.0 times 10 to the negative 7th meters, and our red light is 7 times 10 to the negative 7th meters of wavelength. And we can categorize our different electromagnetic waves to be different types of light, some of which we can see because our eyes can process visible light. Other ones we can't see with our human eyes. So let's talk again about how we can take this one step further and now find the energy of our different waves. Our electromagnetic radiation means light. And light is comprised of photons. Photons are the particles in light that behave also as a wave. So, like what we talked about in class, photons have particle wave duality. They behave like a particle and like a wave. So we can describe the energy of our photon, which is a particle property, from the light of our electromagnetic spectrum. And what we're able to say here is that the energy of our photon, E equals the energy of our photon, is equal to this value H, which is known as Planck's constant, times our frequency, or nu. So our Planck's constant is this value right here. Of course, on an exam, like you would on the AP chemistry exam, you're going to have all the constants given to you, so you don't need to memorize these. But if you're asked to solve for the energy of our photon, we know Planck's constant and we know our frequency, so we can, or you'd be given your frequency and you'd be asked to solve for your energy of your photon. But what we can do, right, since I know that there's a relationship, C is equal to lambda times nu. I can say that nu is equal to C divided by lambda. And if I now take this right here and I plug it in to nu right here, we end up getting this second relationship, which says the energy of my photon is equal to Planck's constant times the speed of light divided by lambda. So the way we express the energy of our photon, we have two different ways. The first way is if we're given our frequency, So it's our frequency relationship. And our second equation that we have is our wavelength relationship. So let's go ahead and wrap up this video talking through some practice problems. We're told that a laser emits a frequency of 4.74 times 10 to the 14th inverse seconds. And we're asked, what is the wavelength of light in nanometers? So let's identify our givens. We're told that the frequency is equal to 4.74 times 10 to the 14th 1 over seconds. We're asked, what is the wavelength? In nanometers specifically. And we kind of look through our archive of different equations. We know that C is equal to lambda times nu. We know that the energy of a photon is equal to H times nu, and that's also equal to HC over lambda. Between these equations, based off of what we're given and based off of what we're asked to find, I have to utilize this first equation. I know it's that first equation because I'm not asked anything about energy of the photon. So what I'm able to do now is say that my wavelength is equal to C divided by my frequency, because I divide my frequency from both sides. I plug in 3.00 times 10 to the 8th meters over seconds divided by my frequency, which is 4.74 times 10 to the 14th 1 over seconds. Numerically, I get as my answer 6.33 times 10 to the negative 7th. And now I go ahead and I check my units. My seconds cancel with my seconds, so I'm left with my units of meters. Numerically, this would be a correct answer, but I'm asked in nanometers, so I'm going to have to do some conversions. I know that there's 6.33 times 10 to the negative 7th meters, and I have to get this into nanometers. What I'm going to have to identify based off of previous knowledge, that in 1 meter, there's 10 to the 9th nanometers. So when I plug that into my calculator, we get that it's 633 nanometers of light. Now, if this last step, you saw me do that, and you're confused with that, this is my reminder that you should go ahead and review your prefixes that you've learned in a previous class. I've also attached a Khan Academy video that I would recommend you watching if that step was confusing and if you didn't remember where that 10 to the 9th value came from. So we just went ahead and solved for this problem. That means that 633 nanometer wavelength of light has a frequency of 4.74 times 10 to the 14th inverse seconds. Last but not least, it's asking what is the energy of that photon of light that we just solved for. So we know here that we have two different equations to solve for the energy of light. We know that energy is equal to h nu, and I also know that energy is equal to hc over lambda. Based off of my information given, I'm given my frequency. So I'm going to want to go ahead and utilize this first equation and not the second. The realization is that we're given information about the frequency. You could do one extra step and solve for the wavelength, like how we just did, and then plug in the wavelength. But based off of the information given, let's go ahead and utilize our first equation here. So I know I'm solving for my energy. Planck's constant is equal to 6.626 times 10 to the negative 34th joules times seconds times my frequency that I'm given. And when I plug that into my calculator, my seconds cancel as units. So I'm left with my energy as 3.14 times 10 to the negative 9th joules. This is kind of the first time, at least in this class, that we've seen this unit, the unit of joules. This is going to be our common energy unit that we're going to see throughout the entire class. Another thing to specify is that when we're thinking about significant figures or significant digits, we don't ever incorporate constants into our potential for our determination of how many sig figs to report. So I know that Planck's constant has 4 sig figs here, but we treat that as a constant and treat that as if it's just one value. So we're going to want to identify that our frequency has, 3 different significant figures. So my answer is reported in 3 significant figures. We never utilize a constant in terms of determining our overall sig figs of our answer. So that is it for this lecture video, and I will see you in the next one. Bye, everyone.